Computers have changed the world immeasurably in a very short time. Their abilities to do complex calculations and retain information is a key part of many modern technologies. At Mary Baldwin University, students in the physics department have been working on ongoing research into fabricating and analyzing a new nanoelectronic component called a memristor. Memristors act like the switches in traditional computers, which are called transistors. Unlike transistors, however, memristors also have memory. Therefore, a memristor is an electrical nanotechnology that has the ability to act as a resistor with memory. This means that they hold their state, they use less space, and you can incorporate more devices per chip. They are also more efficient because they store memory in the same place where they compute. This leads to an abundance of possible applications, such as biologically inspired computing, non-volatile memory, and hybrid circuits of transistors and memristors. At Mary Baldwin, undergraduates in the physics department have been working with flexible memristors that are inexpensive to fabricate. Physically flexible memristors not only have the same qualities as rigid memristors, but are also less fragile, still being operable after being flexed 4,000 times, able to be fabricated using inexpensive room temperature solution processing, and operable at voltages of less than 10 volts, which is a relatively low power for flexible electronics. Flexible memristors have potential uses with lightweight, portable electronics such as glucose monitors. These flexible memristors are made by using an inexpensive flexible polymer sheet, then adding a bottom metal contact, applying a titanium dioxide sole, and spinning it on so it is just tens of nanometers thick. This sole then reacts with water in the air, which is a reaction called hydrolysis, to form a titanium dioxide sole gel. Then, finally, another metal contact is placed on top. Special equipment is used at Mary Baldwin University to electrically characterize these memristors. This equipment consists of a probe station, which has tiny probes that are used to contact the surfaces of the memristors, and a semiconductor parameter analyzer to then measure very small electrical signals. With these, one can apply a voltage to the memristors and measure their electrical behaviors. Like a traditional transistor, memristors can be switched from off to on by applying an appropriate voltage. Memristors start out in a high resistance state that allows very little current through, meaning the device is off. This is represented by a logical 0. Once a high enough voltage is applied, the device switches to a low resistance state and more current can flow through, meaning the device is on. This is represented by a logical 1. The device will stay on even when no more voltage is being applied and will remain on until an adequate negative bias is applied that will turn it off again. So why does a memristor switch? The present theory is that this switch is caused by drifting of positively charged ions or vacancies within the titanium dioxide insulating layer when the bias is applied. These vacancies can either be created manually or can occur naturally in the gel due to imperfections when it is made. Applying a bias to the metal contacts either attracts or repels the positive ions, and this is what causes the devices to be on or off, and can be switched continuously between the two. One undergraduate student chemically synthesized the sole for the memristors in the lab at Mary Baldwin University. She then used spectroscopy to show that when this sole was spun and hydrolyzed, it resulted in the desired titanium dioxide sole gel film. In addition to memristor fabrication, students have been working on memristor circuit simulations using a software called LT-SPICE. This software can be used to simulate circuits formed by wiring together transistors to make gates. Digital logic gates are the computational foundation of our current computers, and the ability to simulate these gates is essential to computer design. The LT-SPICE software, however, does not have a memristor component to enable memristor circuit designs. The students working in the physics lab with Dr. Gergel-Hackett were able to design a memristor model that showed the expected switching with memory. The result of a correctly working memristor would look similar to this. These modeled memristors can be combined to realize new computing paradigms such as material implication. Material implication, or imply gates, have the potential to be used to achieve all traditional computing gates, but because they are new computer architecture using memristors, they will be much faster. Because our imply gates will be made entirely of memristors, the advantages of memristors, such as logical computing and memory together, fast internal communications, and high efficiency, apply as well. Research with this memristor model is currently being continued by physics students at Mary Baldwin. Computers impact our lives in so many ways, it is hard to imagine the world without them. Researchers are always working to develop new, innovative systems that will make computers better and our lives easier. Memristor research is at the forefront of a new era of technology.